In section 2.4, we talk about proof by cases. So proof by cases is something that works in only specific types of problems. So if you try to prove something and it doesn't work to prove it directly and it doesn't seem to work to prove by contrapositive, it might be a good idea to look for any cases. As an example, say we wanted to prove or find a counterexample to the statement, if n is an element of z, then n squared plus 3n is even. Okay, so we don't know right off the bat whether it's true or false, so it makes sense to try some values of n and see if it's true. So we're going to look for some n that are elements of z, that are integers, and see if it's true that n squared plus 3n is even. So when n is 0, we have that n squared plus 3n would be 0 plus 3 times 0, which is 0, which is even. If n is equal to negative 1, then this expression would look like negative 1 squared plus 3 times negative 1, which is 1 minus 3, which is negative 2, which is even. Okay. If I tried n equals 2, I'd get 2 squared plus 3 times 2, 4 plus 6, which is 10, which is even. If I tried 7, I'll get 7 squared plus 3 times 7. Let's see, that's 49 plus 21, which is 70, which is also even. Okay, so I haven't been able to find a counterexample yet, so it seems to be true. But how do I prove it in general? Because if I wanted to go ahead and prove this directly, I would be assuming n is an integer and proving n squared plus 3n is even, so it can be expressed as 2k for some k. How am I going to get here if all I know is that n is an integer? Okay, well this is where it might make sense to break it up into cases, because if I knew that n was even, then I could say n is expressed as 2 times an integer, and then I have something to work with over here to prove this side is true. But I don't necessarily know that n is even. It could also be that n is odd. One of those two things has to be true because every integer is either even or odd. So what we can do is try to break up our assumption here into two cases, and in both cases try to conclude that n squared plus 3n is even. If I can do that, then I'll know that this statement is true for every integer n. All right, so just as a reminder, what we're trying to prove is if n is an integer, then n squared plus 3n is even. All right, so proof. We're going to assume n is an integer. Every integer is either even or odd. Which means one of the following must be true. Either 1, n is even, so n is equal to 2k for some integer k, or case 2, n is odd, which means n can be expressed as 2j plus 1 for some integer j. Right, so what we're going to do is prove this in two cases, and in both cases we will show the conclusion is true. We will show that n squared plus 3n must be even. All right, so case 1. N is even, so n is equal to 2k for some k and z. All right, if this is true, then what can we say about n squared plus 3n? Then we would have n squared plus 3n is equal to, well, n is equal to 2k, so this would be 2k quantity squared plus 3 times 2k, just substituting in 2k for n. If I expand this out, I get, let's see, I get 4k squared plus 6k, and I'm trying to show that this expression is even, so I want to express it as 2 times some integer. So I just have to factor out a 2 here. This would be 2k squared plus 3k. Great, that's pretty much it, right? I know that this is going to be an integer, right? This k is an integer, so 2k squared plus 3k is an integer also. And so now we can say by the definition of even, n squared plus 3n has been expressed as 2 times an integer. So n squared plus 3n is even. Great. So case 1 is done. We assumed n was even, and we proved n squared plus 3n is even also. Now, if we can also do the same thing for case 2, then we'll know that it's true for every integer, because every integer is either even or odd. Case 2, n is odd. So n is equal to 2j plus 1 for some integer j. All right, then we would have that n squared plus 3n is equal to, we need to substitute in 2j plus 1 here. 2j plus 1 squared plus 3 times 2j plus 1. This is going to be a little bit messier to expand, but it's just algebra. 2j plus 1 times 2j plus 1, when we FOIL or distribute it out, we get 4j squared plus 4j plus 1. And then if I distribute 3 inside the parentheses here, I get plus 6j plus 3. In combining my like terms, I end up with 4j squared plus 4j and 6j is 10j, and 1 and 3 gives me 4. I want to show this is even, so I want to show that it's 2 times an integer, so just factor out a 2 here, which we can do. And now this is sort of the integer that you were looking for. So since j is an integer, we have that 2j squared plus 5j plus 2 is also an integer, which means by the definition of even, we've shown once again that n squared plus 3n can be written as 2 times an integer. So n squared plus 3n is even. Right? Now, since we have proven both cases, since we have shown in both cases that n squared plus 3n is even, the statement is true for all integers. And we're done. Okay, so notice, when you're trying to prove something about all integers, which is what we were trying to do here, right, in this first example, we were trying to show for all integers that a particular statement was true, that's a good candidate for proof by cases because we know that we can split the integers into evens or odds. But sometimes it doesn't actually help to split into even and odds. Right, so before we go on to the next example, I want to just introduce an important idea that's going to help us in some of these cases problems, and that's the idea of modular arithmetic. So we've seen that for any integer n has to be even or odd, which means that we can express any integer n as either equal to 2k for some integer k, or 2j plus 1 for some integer j. So this is really just a way of formalizing the notion that any integer is either going to be divisible by 2 or not divisible by 2. So if you take any integer and you divide it by 2, the result is either going to be a whole number when n is even, or it's going to have a remainder of 1, right, that's your plus 1 here, if n is odd. And so a good follow-up question would be, can we generalize this idea to divisibility by other integers other than just 2? And we can, okay? So let's look at divisibility by 3. When we divide an integer by 3, what must be true about the result? Okay, well, either you get a whole number, right? If 3 divides n, if n is in fact a multiple of 3, then dividing n by 3 is going to give you a whole number. Or if n's not a multiple of 3, then you'll either get a remainder of 1 or 2. Which means for any integer n, we can break it up into 3 possible cases. Either n is equal to 3k for some integer k, right? So this is basically saying either n is a multiple of 3, or you'll either get a remainder of 1 or a remainder of 2, which means we can express n as 3j plus 1 for some integer j, or as 3l plus 2 for some integer l. I've really just generalized the even and odd argument for divisibility by 3 instead of divisibility by 2. Right, so in the divisibility by 2 case, it was either divisible by 2 or you could express it as a multiple of 2 plus 1. Now you have 3 cases. You're either divisible by 3, or you can express it as 3j plus 1, or you can express it as 3l plus 2 for some integers k, j, and l. Okay, so we can formalize this idea with what we call modular arithmetic. If an integer n is divisible by 3, we would write that n is equivalent to 0 mod 3. Actually, the parentheses go around the whole thing. Which just means that when you divide n by 3, you get a remainder of 0. Right, this means n divided by 3 gives a remainder of 0. Which is just another way of saying n is a multiple of 3, or n is equal to 3k for some integer k. Okay. If dividing n by 3 gives you a remainder of 1, we would write that n is congruent to 1 mod 3. And this just means when you divide n over 3, you get a remainder of 1. And another way of saying that is to say that n can be expressed as 3j plus 1 for some integer j. And finally, if dividing n by 3 gives you a remainder of 2, we would write that n is congruent to 2 mod 3. And this means n over 3 gives you a remainder of 2, which is like saying that n can be expressed as 3l plus 2 for some integer l. So it's the same 3 cases we saw before, it's just another way, another notational way of expressing that. Okay, and so as an example, let's say we wanted to express each of these numbers n, 14, 35, 22, and 121, as congruent to either 0, 1, or 2 mod 3. So essentially what we want to know is the number on the left a multiple of 3? Because then it would be equivalent to 0. Or is it 1 more than a multiple of 3? Because then it would be equivalent to 1. Or is it 2 more than a multiple of 3? All right, well 14 is definitely not a multiple of 3. So we just have to think, what's the nearest multiple of 3 that's smaller than 14? That would be 12. Right, we can write 12 or 14 as 12 plus 2. And this here is a multiple of 3. Okay, so because we have this plus 2 at the end, 14 is equivalent to 2 mod 3. All right, how about 22? So 22 is not a multiple of 3, but the nearest multiple of 3 would be 21. Whoops, so we can say that 22 is equal to 21 plus 1. That is 3 times 7 plus 1. And so this plus 1 at the end means 22 is going to be equivalent to 1 mod 3. 35, is 35 a multiple of 3? No, it's not. It's the closest one would be 33. It's 33 plus 2, or 3 times 11 plus 2. Okay, so this plus 2 at the end means 35 is going to be equivalent to 2 mod 3. And finally, 121 is not a multiple of 3, but the closest one would be 120. So 121 is 120 plus 1, so that's 3 times 40 plus 1. And that plus 1 means 121 would be equivalent to 1 mod 3. So I didn't get any zeros here, but if you had tried something like 63, 63 would be equivalent to 0 mod 3, because 63 is itself a multiple of 3. It's 3 times 21. Okay, so hopefully we get the idea of what's going on here. The key takeaway is that for any integer n, you can break it up into one of these 3 cases. It's either equivalent to 0 mod 3, 1 mod 3, or 2 mod 3. All right, now let's extend this to divisibility by 4. Okay, sort of analogously, we're going to be able to split this up into 4 cases. The first case would be n is equivalent to 0 mod 4, which essentially just means n is itself a multiple of 4. Or n is equivalent to 1 mod 4. That means when you divide n by 4, you get a remainder of 1, which means you can express n as 4j plus 1 for some integer j, or n is equivalent to 2 mod 4, which means when you divide n by 4, you get a remainder of 2, which is like saying n can be expressed as 4l plus 2 for some integer l. Or finally, you could say that n is equivalent to 3 mod 4, which means you can express n as 4 times m plus 3 for some integer m. Right? Same thing with 5. You can break all real numbers or all integers up into what is their remainder when you divide by 5. It'll either be 0, 1, 2, 3, or 4. Okay, so sometimes when we're doing proofs, you'll have to worry about breaking up the integers into more than 2 cases, not just even and odd, but maybe what is the remainder when you divide by 3, or what is the remainder when you divide by 4. So we'll see some examples of that in the next video.